Hello and welcome everyone. Thank you for joining us today for the We Let Our Developers Choose Their Own Kubernetes Requests and Limits and This Happened webinar. Because yes, we do recognize that some things are just better left to machines. My name is Daniela and I'll be the moderator for today's session. I'm excited to introduce Andrew, CTO and co-founder here at Densify. Hello, Andrew.
Hello, everyone.
He will lead today's session and take us through some key factors of optimizing Kubernetes, as well as a few customer examples. And with that, I'm going to pass the mic on over to Andrew to get us started.
Thank you very much, and thanks everyone for joining. Yeah, today, Kubernetes, what happens when you choose the wrong requests and limits. It's part of our series of tabloid headings on our webcast. The next one's going to be, I was abducted by an alien, and I saved cloud cost as a result. Let's dive right in. Let's talk about the challenge in containers. This is really at the heart of it, is that there's a lot of settings to choose when running a container, more so than in a cloud instance or a VM even, in a legacy environment. You see here, we've got a little snippet of a manifest saying we have memory requests, memory limits, CPU requests, CPU limits, all these obscure numbers in strange units. And the challenge we see is that it's really hard to set these correctly. And it's not because people are stupid or they don't know what they're doing. You probably don't have the right data. You probably haven't seen your app run enough to know what it's going to do. You're probably just guessing at the start. And a lot of times you deploy these things, put them in the wild, and you don't go back and look at them because everybody's too busy. This engineer is probably off writing the next thing or developing the next feature or app because somebody's pounding their fist saying, let's get more functions out there. And so nobody has time to go back and revisit all these numbers. And they're usually wrong, and they're usually quite wrong. And I'm going to talk a bit about how quite wrong they are. We talked about kind of having some case studies here. I'll show some anonymous examples of analysis. Everything in here is real. Even this one is real. This is an example of a container. This is the 24-hour utilization of that container by quartile. So the little thin part is the peak, and the thick part is what we call sustained activity. And the way you read this is the request is 2,000, so it's 2 CPUs. So somebody gave this workload, this container, 2 CPUs, but it's barely even using a half a CPU. I mean, it's peaking at 3/4 of a CPU. The request and limit are set to the same value. That's also rarely optimal. So, this one's just way too big. Somebody gave it, I'll talk in a minute what this does, but it's been given too much resources. Here's another example where the container memory is hitting 3 gig, but it was only given 1 gig. So you didn't request enough for this thing, and you might run fine or you might not. I'll show an example of this as well, what happens here. And this can be in the same container, and the limits can be wrong in the same container. Everything can be wrong. You see here, this memory limit on this one is very close to the peak memory usage. That's also very dangerous because if you want to use a bit more memory, you'll get killed. And I'll show an example of that. So all kinds of things can go wrong in a container, even one container, and usually companies have thousands or tens of thousands of containers, even up to 1 million. We've seen over 1 million containers. And the problem is really, as you guessed from the title, we don't feel humans should be doing this. It's not a good use of their time, and it doesn't work very well. If you set things too low, let me dig into this for a second. So let's just say I have a memory usage pattern that looks like this. I know most memory patterns don't look like this. It could be busy at the end of the day or end of month. It doesn't really matter what the metaphor is. It's like a Tetris block that looks like this, for argument's sake. And when I place that on a node, so the blue square is the actual Kubernetes node you're running on. Picture it being a scale group node or just an instance. If I run that on there, but I only ask for, say, 1 gig of memory, but say if this thing's using 1.5 or 2 gig of memory, and what will happen is Kubernetes doesn't really know what that peak red thing is. It only knows that you gave it 1 gig, and it's going to think there's 3 gig left on that box. And it's going to keep stacking workloads until it's given out the 3 gig or whatever the case is. But in actuality, the usage is above that. And if all these things use their memory at once, the node runs out of memory and something gets killed. So, this happens. I'll show examples of this happening. So if you happen to not give things enough resources and they fall on the same node as other things that don't have enough resources, you got a problem. At the same time, if I have something that's using kind of a flat memory usage, maybe pretend this isn't 0, just pretend it's kind of a flat usage or a certain level of usage, but I ask for way too much. Let's just say it's using 1 gig and I ask for 2. Kubernetes will say, well, okay, there's another 2 gig left in this machine. We'll put 1 more of them on there, and then we're done. We're going to move on to the next node. This is key. So Kubernetes does not overcommit the way a VMware hypervisor would. It's not going to give the same resources out to multiple containers. They share at runtime. They can steal from each other. But once I've scheduled all the resources on a node, Kubernetes will go and start a new node. And so, but in actuality, less than half this node is being used. So you can see here the way the chips fall. You could have some nodes that are 3 times busier than the others. In this PowerPoint metaphor, in the real world, it's even worse than that. But just kind of to exemplify the problem. And again, this can be happening both can happen at the same time. You can have some nodes that are overstacked, some that are understacked. If the yellows and the reds fall together randomly, you might save yourself. You might have something that can get busy because something else isn't using all its resources. But if you get unlucky like this, you're gonna have a lot of waste of money and a lot of risk at the same time. That's the problem with it being, too high and too low. How we solve this, I'll go talk a little bit about how we treat this from an algorithm perspective because it's pretty important, and then I'll show some examples. So the way we feel is best to solve this is to take a very deep mathematical approach to this problem, get all the data, get all the gory details of what this thing is doing. We get it from Prometheus, Node Exporter, various sources, and then learn the pattern of what's happening here. And this is important. So this thing, they could be random, stochastic, they could be very deterministic, very repeating. It all depends on the workload. So we have very deep policy saying, well, let's go back through time. Let's go back through 95 days or whatever the workload range is, using different algorithms to figure out how do we model the workload pattern, the 24-hour pattern of this thing. And the curve at the top is multiple days. But what we can do is say, okay, let's go through this. And one of our main algorithms, we have several, is what we call combined. I nickname it the Jiffy Pop algorithm because it'll go through and kind of build an outer envelope of what this thing does. Just to get really detailed for a second, if I take the midnight to 1 a.m. time slice across all my history, we were showing whatever 6 days here, but pretend it's a big history, I can then go and use that to build a statistical model of what that thing typically does from midnight to 1 a.m. And of course, if I then slide through time, I can build a model of the outer envelope of operation of this workload. So this is a representative model of what this container typically does. And like I said, it could be very repeating. It could do the same thing in the same pattern every day. It could be random, in which case this will reflect that. It'll say, okay, we don't know, it's crazy Ivan. We don't know what it's going to do. It could go up to 2 CPUs or it could stay idle. And so it's important to model that correctly and statistically what this thing is doing. And then we can see the peaks and the sustained activity, which are absolutely critical for sizing these containers. And it's critical because you don't want to just size the peak, and you don't, again, it's a function of these things depending on how you want this workload to behave. So on that front, then we say, okay, we've got the peaks and sustained. Now, let's just say this thing was given 2 CPUs. That's pretty high. Like I said, if you give this 2 CPUs, then those are locked on that node. Other people can use those CPUs when this container isn't, but you're not going to give the same 2 CPUs to a different container as well from a scheduling perspective. And this is too high. If you're requesting above peak, you're just stranding a whole ton of capacity. All that white space below that yellow line is going to be just chewed up for no good reason. So there's deep policy as well on how you treat that. Well, in this case, we're saying, well, we want the sustained activity to hit 80% of our request value. If you run the math on this and you kind of do it, and of course you do it across all the thousands of containers, this particular one, we're saying the request should be somewhere around 600 millicores. The limit should be pretty high. We don't want the limit clipping the workload, but we don't want it really, really high either. There's this kind of sweet spot for the limit. And if we do this, then this will stack higher. If I do this to all my workloads, of course, I've chopped the request value way down. Kubernetes is going to put 3 or 4 times as many containers on each node, but safely, because we know that we're mostly not using those resources. We do peak above those resources, but it can borrow from others when it does that. That's the best way to run an efficient Kubernetes environment. So we can come up with the optimized requests and optimized limits, again, using math and patterns, and make sure that we have this, kind of hit the sweet spot of how we're scientifically doling out resources to minimize risk but maximize efficiency. And again, if you put that yellow line way too high, it becomes extremely expensive. Kubernetes environment will be, the scale group it runs in will be huge and very, very expensive. That's not all, because let's just say, a lot of cases we find that there's the containers are highly replicated. So they could be, one of those running or 2 of those running, or there could be, in this case, upwards of 300 running based on the time of day. So we also get the pattern of replication, the pattern of the number of containers that are running, and that all factors into the model as well. So this model becomes a composite model of all of the containers, all the replicas that run. So again, it's just a little next layer on the model saying that the peak is the peak of peaks, and you can program how this behaves. But the model says, no, this is an aggregate model of all the workload, because there's only one recommendation for the replica set. There's only one request and limit value that they all inherit. So it needs to be a very smart function of what all the running nodes are. So that's done as well. So this model actually is a composite of all the replicas. That's important to do. And so I'm just laying out what we consider to be the important aspects of getting these numbers right. And the last thing I'll mention is you might also have microservices or ephemeral workloads that kind of come and go very quickly. They can be difficult to deal with because they're gone and they have no context anymore, but they might be off the same launch configuration, part of the same workload, just a very fragmented workload. So we also can take these fragmented snippets of utilization and do what we call stitching to say, okay, that's really what that workload looks like. And so because we have a launch configuration, a manifest that this thing launches off, we can optimize the numbers in that. even though the container might only run for a very short period of time. The challenge there is it seems like it's not a problem if a container runs for a few minutes and it's way bigger than it needs to be because it only runs for a few minutes. But if you have thousands of those running, then it becomes a source of cost as well. So even though they don't run very long or even things that aren't very big, if there's a lot of them, it starts to add up. So that's how we treat the challenge. If you look at an example, this is the UI. Most people access this API, it's all API accessible. So you're not going to necessarily use the UI to look at 10,000 containers, but you can go in and see certain things and see how it's working and spot check things. If you want to get someone to take action, this level of detail is very useful, to kind of explain the rationale for the recommendation. And you see here, there's a bunch of different optimizations. If you're familiar with our cloud optimization, which will do, upsize, downsize, modernize, change family, there's more in the container world because you can actually go up and down at the same time. What we call a resize. You give it less CPU and more memory, or vice versa. Or things can be unspecified. So you might be giving something a value that doesn't even have a value already. You can see all the colorful recommendations there. If I pick on this first one, you see it's currently running with 4 CPUs, and we're recommending to bring that down to 3.2 CPUs, but we're also recommending to bring up the limit. And that's kind of evident down here where this one, again, the request and limit are at the same value. That's usually not desirable. You're going to clip the workload, you're going to throttle it above the limit, and the request is leaving quite a bit of white space. But on the right, you see the predicted model with the recommendations. The request is lower, limits higher. This thing's going to be more efficient, and it's not going to be clipped. And again, the details are all here, all API accessible. So in scale, I'll talk about how you automate this in scale in a minute. That's kind of the fundamentals of the analytics being applied. Now, we were going through this one of our bigger customers, and they had, I think, just below 60,000 containers. And they said, this is amazing. This is great to have this level of detail. Can I roll it up to a level like a whole app or a whole group or a whole team? Which is a great question because you don't want to see 10,000 rows. So, if we look at this from a higher level, what we developed based on working with our big customers is a visualization for this. If you look at this example where I've given the workload 1 gig of memory, but it's using 3. So this thing is really a third the size it should be. We should have given it more resources when we deploy it. We can actually plot that on a histogram saying, well, that's down in the kind of roughly 1/3 bucket. So we're kind of bucketing these things saying how much too big or too small or just right are they? So that one's way too small. This one, we gave it 500 megabytes, but it's only using 100. So it's 5 times too big. So it goes over in this bucket. This one looks pretty good. The limit looks really high at 3,000, but the request value is just above the typical utilization. So that's actually a nice specimen of something that's pretty good. We'll put that in the middle. The fourth example I'll show is, here's one that you see there's no yellow or purple line. It doesn't have a request or limit. It's just running and using 3 gig of memory. So it's kind of like dark matter where that runs, the scheduler won't even know what it's going to do, has no idea. And so we chart that on a gray bar over on the left, unspecified, which again can be pretty dangerous in some cases. And if we do this in scale through lovely PowerPoint animations, we get a visual of this that can be any size. We can render this for 100 things or 1,000,000 things, and we can render it for different groupings. So you can look at everything you have, or you can look at all your Nginx servers, or you can look at all your Istio proxies. You can slice and dice any way you want and visualize it this way. So again, for a whole business group, you might get a good idea of how the business group is doing. For a particular app, you get a different slice saying how well are we doing in sizing, our NFS servers or whatever the case is. And you can see the red is, in this case, because I'm looking at memory, if there's too much red, you're at risk of things getting killed, as I described with those Tetris blocks. If you're yellow, you're wasting money. If you have some red and some yellow, you might be getting lucky, depending on how the Tetris blocks land with each other. And then the green, of course, is what you want. So this is a pretty typical looking example where a whole lot is not right, and it's not right in all kinds of different ways. I promised some actual examples. This is a visualization of about just under 15,000 containers, everything running in one of the cloud providers, all the Kubernetes in a real world situation. And the top left is the CPU request visual, the top right is the memory requests, and CPU limits and memory limits. If you look at the CPU requests, the glaring thing here is that almost 5,000 containers are over 5 times bigger than they need to be. 500% is 500 and more. So you could be 10 times too big. You could be 20 times too big. So there's a whole lot, now they could be small, they could be big. You can see that in a different view. This is not saying how big they are, it's just saying the number of things that are wrong is staggering. And that will create a tremendous cost. You're going to be over provisioning because, like I mentioned, the Tetris blocks, you're asking for way more than you're using. You're just going to run more nodes than you should be. There's also almost 1,000 containers that have a fifth or less of the memory that they need, which is just particularly scary. But at the same time, there's a whole lot that have way more memory than they need. So you might be getting lucky, or you might not. I'll drill into that in a second. Memory limits, the gray bar here is pretty dangerous. You didn't put a limit on the memory, so if you have a memory leak, that thing is going to run out of control and kill a node. I'll talk about those other red ones in a second. Zoom in on this 200% on the top left. So the 500% is obviously pretty nasty, but even the 200%, those are things that are twice as big as they need to be. But let's kind of look at an example here. So here's a real world example. Just focus on the numbers here, some Tomcat servers in this case. The first one has 9,000 CPUs. We're saying that it needs 90. So whatever that thing is doing, it's not doing anything. It's kind of wasting 9 CPUs. And the second row down is wasting almost 9 CPUs, just a little bit less. So those are pretty egregious. That's obviously not a great situation. But what I want to focus on is this next one down here. This is the highlighted one. This one's 9,000, and we're saying it should be around 5,000. So there's about 4 CPUs of waste. So not as bad as the first two. And you can see down here, the pattern is sitting right around 4,000, 4 CPUs of usage, up and down a bit more than that. And the request is 9,000. So all that white space below the yellow line is just wasting money. But in this case, there's 112 replicas. I think we've even seen worse than this. Like this is just kind of a typical, there's 112 replicas, all 4 CPUs too big. So the math shows it's 455 CPUs of pure waste from one container. This is all running off one launch configuration. So there's a Terraform file, some manifest file that's just got wrong numbers in it, and it's equating to about just under 200,000 US dollars a year for that one line item. We love to focus on this because there's a kind of 80-20 rule. There's a few offenders that usually add up to a whole lot problem in any given environment. In this case, just this one line item is a pretty big win to stop that from doing what it's doing. If you have sufficient history, you got to make sure you have a business cycle and you understand what this thing's doing at peak, which is all part of our policies to make sure that, nope, we've never seen it go above that level. And this is a very safe recommendation. That's a good example. Let me talk about memory for a second. In this case, we have equitable waste in both directions. And what does that do? So Kubernetes relies on those numbers to start, as I mentioned in the Tetris example, to start the containers. So here is that environment. It's part of that environment with a bunch of worker nodes. I think this had 72 worker nodes. And this is the average and peak memory of those worker nodes. And if you just scan down the list, you see it's kind of all over the place. 18, 74, 99. And if I sort that from highest to lowest, you see a whole bunch of the top ones are hitting effectively 100%. You can't really hit 100% because things get killed. So once you're up in the 98, 99 world, you're basically pegged at the limit. And if I look at the top one here, this is what it looked like. So this is a 24-hour memory usage where once you hit 4 p.m., you were just hitting the roof, and things were getting killed in this environment because of that. At the same time, if I scroll down to the bottom of this list, the bottom one was only using 15% of its memory. And even the ones above it, 18%, 19%. This is the same cluster, same node group. The scheduler just doesn't know what to do because you're giving it garbage. If you give it the wrong request values, it'll just do whatever, throw darts. And so the same environment was wasting a ton of money with stranded memory and had out-of-memory kills happening on the nodes. Back to the title. This is what happens when you let developers or engineers choose their own requests and limit. It's not that they're incapable of it. They don't have the information. They don't have the context to do that, and they don't have the time to revisit it and make sure it's correct. So garbage in, garbage out. And like I said, these ones at the top right here, once that node started bouncing off 100%, things just get killed. It's called OOM kill, out-of-memory kill in the container environment. I'll talk about one more example off this one. These red ones down here, I mentioned the gray down here is pretty bad because you're not giving it a limit. So if something gets a memory leak, it could blow up a node. Even worse are these red bars here. There's not many of them, but we see them, and they're really dangerous. Those are the cases where a workload is running above its limit. So if the limit's too low, for CPU, if your limit's too low, you get throttled. For memory, if your limit's too low, it's not an elastic resource, you get killed. So if you go above your limit, you just get whacked by the scheduler, Linux kernel. Here's an example in that environment, same example, where this is a very interesting workload curve. It's the memory usage curve over a day. You see here a bit of a disruption. This thing got whacked on the head, kind of staggered back up to its feet and got going again and got whacked again. And the peak it hit was 952 meg, and the limit was 953 meg in the configuration. So this thing was just staggering to its feet, getting killed, staggering again. It seemed to settle on some lower level, probably in some degraded state at this point because it's been killed so many times. This is a real problem. Even though containers, they'll restart. They're cattle, they're not puppies. They can be killed and restarted. This disrupts things. This makes queues fill up. It disrupts the response times of the apps. It should not be happening. So this is just by setting the wrong limit and throwing it out in the wild, this was just happening. And it's hard to see because there's 50,000 of these containers running and nobody has time to go look at all these the Grafana curves for all of these things. Here's an example of automating it. So we feel that if you have the right answer that's really sound from a mathematical perspective, sound algorithms, a lot of history, a lot of policy, then you can just automate it. This is an example of a customer that basically every time they deploy, we'll go hit our APIs to get the proper requests and limits and put it through their process. It's into basically OpenShift templates and optimize the deploy every time. And they negotiate with change management. They don't need a ticket to do this for the containers. They can just inform change management. As a result, I believe they chopped their infrastructure spend in half in the container environment, and they have some of the cleanest curves you've ever seen. These are beautiful histograms. It's not all green. One of the reasons is because the policies don't make too big a change at once. You can tell it, don't go crazy and take away 90% of my resources, just take half away at a time and iterate. So you can get some residual yellow and red just because you want to be safe when you're automating and not make too drastic a change. This is a great example of really good, called hygiene. There's no gray bars. All the requests and limits have a value, and they're all really good values for the most part, and it's all happening automatically. Some resources here. GigaOM just released a radar report for cloud resource optimization, where we were nicely named as a leader and an outperformer in that area. We love that, especially because containers typically run on the cloud, and everything I've described, when you optimize the containers, we then optimize the scale groups and the instances in line with that. So that's how you actually get your save. We're considered a leader in the cloud world. They have a similar report from 2022 as their latest for Kubernetes, and we are also leader in that one. So I don't have a link to it here, but if you look for it, their Kubernetes resource management report, we also are in the center of that as well. We're pretty proud of that. And the last thing I'll mention before I head back is that we are also offered by Intel as Intel Cloud Optimizer. We have a great partnership with Intel. They recognize the same need for resource optimization and choosing the right instance, automated instance selection in the cloud and for containers, optimizing the resources. So if you qualify, you can get actually a full year of usage of our software through Intel. They'll sponsor it. And there's cloud offering. There's also container offering. If you're interested in that, there's a QR code here to get more detail. Great program.
Thank you, Andrew. We do have an upcoming webinar on August 10th. It's going to explore cloud and Kubernetes tagging best practices, and our speakers will cover the importance of tags for optimizations as well as a live demo. Some resources that may be of interest. We do have a poster available for download, and it does cover the histograms that Andrew had mentioned earlier and the visualization of 12 risks associated with Kubernetes resource management. And also, this is exciting, we have recently launched a podcast, and it is actually hosted by Andrew himself, and it focuses on interviews with IT and technical leaders. Each episode dives into conversations about their careers, as well as insights into the latest cloud trends and best practices. We have a couple of episodes live right now with leaders from FactSet, Liberty Mutual, and our latest one from Intel. So you can go ahead, scan the QR code, and check that out. And lastly, if you're interested in learning more about Densify and keeping up with the latest news, just do go ahead and follow us on social. And I will hand it back over to you, Andrew, for any questions.
Yeah, there was one, and I will mention I'm using my podcast mic right now. It's really worthwhile to invest in a nice mic for all of these things. There was one question. I think it might have been answered by the content. It's a great visualizations. Does it auto-remediate the limits or just provide the dashboard? And absolutely, we auto-remediate. It's not just a push button and go and change the Kubernetes settings, because it'll just go back to whatever is in the manifest file. So unlike a VMware environment, you can't just go and resize things and have it stay that way. In cloud and in container, it's all coming from something like, for example, a Terraform file. And whatever's in that file, it will just become again. So no matter what you do to the running instance, it'll go back to what's in the file. So you have to go upstream for it. And we have a Terraform module, for example, that lets you put a line of code in a Terraform file, and that gets the data from our API and will automatically do it upstream. So if you picture a DevOps pipeline, you have to kind of inject the optimization upstream. And we have lots of diagrams. We probably covered webcasts on this as well. And then it will make it so in the field. But if you just go change something that's running, that will not stick, because it'll just reset to whatever is in the manifest file. So absolutely, we auto remediate, but we do it through the pipeline, not just as a kind of easy button, go and change the thing in the field.
That's it. That wraps up today's session. Thanks for joining us, everyone, and we hope to see you on the next one. Bye.
Yeah,
Thanks, Andrew.